Strategen's head of global strategy for Strategen, which is an energy systems transformation consulting firm. Great lineup today that we've got, as Teru's mentioned, and looking forward to getting into that. So if we can just go to the next slide, please, Teru. I guess as has already been mentioned, we've got Jenny Rees from AEMO, David Edwards from Horizon Power, and Goran Strobic from Imperial College in London. And just want to direct you to slido.com as well. So we will be taking questions through Slido. The event code details are there on screen. So ESIG-2B to submit your questions. And please do keep track of those as we go through the content. Answer questions as we proceed. We'll be dealing with questions at the end, but please use it as a bit of a stream of consciousness as we go forward, and then vote up the questions that you think are the most critical that we get to in the Q&A period as well. And if we can go to the next slide, please. So, as has been mentioned...
I didn't quite catch that. Could you please repeat it?
Sorry, I've got Siri telling me that it wants to talk to me. Apologies. So as Teru's mentioned, Australia really is on a very significant trajectory in terms of decentralisation. This graphic from Bloomberg, I think, says it all with regard to the kind of decentralisation ratio that is plausibly the nation is on. By 2050, this is saying that in the order of 40 to 50% of our volume, annual volume, megawatt hours being supplied by distributed resources. And so if we just go to the next slide. Essentially what that means really is that as we think about that transition, we're moving from what has been a highly centralised fossil fuel one-way delivery system, providing a commoditised service to largely passive consumers in the 20th century, to a decentralised, digitised, low-carbon electron transaction system that's ultimately orchestrating millions of privately owned energy resources and providing almost infinite consumer choice. So it's a monumental transition from the 20th century into the 21st century. Next slide, please. And the last thing that I just want to, I guess, highlight here is that as we deal with that kind of transition, obviously we're dealing with a very interesting transition for the sector where DER's really the original focus has been minimising the impact of these new technologies and moving them to the right on that spectrum from minimise harm to help where possible, to ultimately playing an integral role in the future of the end-to-end power system. And so our three speakers today will give Australian insights and also insights from the UK on what it takes to actually enable that systemic transformation. So if we can go to the next slide, and I'll introduce Dr. Jenny Rees from AEMO, the Australian Energy Market Operator. Jenny's Principal Analyst of Operational Analysis and Engineering, previously at University of New South Wales, doing a bunch of well-respected work on 100% renewable power systems. So I'll hand over to you, Jenny.
Fantastic. Thank you, Mark. Let's jump to the next slide, too. So there's a little bit of context about the work that we've been doing at AEMO, looking particularly in South Australia has been a big focus because of the amount of distributed PV that we now have in South Australia. This chart is showing you the minimum demand levels in the South Australian region with the historic values in those grey crosses. And the pink part at the top of the chart is showing you the proportion of energy that's being supplied by distributed PV in those minimum demand periods. Now, a very large proportion. And we're tracking such that operational demand could hit zero or become negative in the next couple of years. So very timely to be looking at what operational challenges may arise and what actions do we need to take now to ensure that we can operate a secure system. And this has been the primary focus of me and my team. Next slide. So there's a bunch of analysis that's been released recently that I'm going to cover in a very brief form for you today. The first is a report to the South Australian Government looking at minimum thresholds of demand and essentially how low can you go with demand before you start to hit challenges, and what are those challenges and how do we address them. The second one is the Power System Frequency Risk Review, where we've looked at how the power system behaves in severe contingencies like a separation event, and how mechanisms like under-frequency load shedding will function with very high levels of distributed resources. And the third one, released most recently, is the Electricity Statement of Opportunities, where for the first time, as well as looking at peak demand, we've also had a very big focus on minimum demand and what that means, where that means there's additional opportunities for stakeholders to get involved, and the sorts of issues we expect to emerge and what we're going to need to do to solve them. Next slide. So across all of this work, there's three key challenge areas that we've identified that start to emerge as you get very large proportions of energy being supplied by distributed resources. And all of these are solvable, but they're things that we're going to need to work through in order to make this power system function with very high levels of distributed resources. The first is around disconnection behaviour in disturbances and how that affects power system security. The second is around having enough load to operate the necessary synchronous units that are providing essential services like system strength and inertia. And the last one is around our emergency frequency control schemes, particularly under frequency load shedding. So I'll talk you through each of these in turn. So on distributed PV disconnection, this chart is showing you measurements that we've taken from a sample of inverters based upon data provided by Solar Analytics. Solar Analytics is measuring individual PV systems out in the network, and across a very large sample, thousands of those systems, we're able to look at how they behave when we have major disturbances on the grid. And this chart is showing you the percentage of those PV sites that we observed to disconnect. They suddenly dropped power to zero in response to a voltage disturbance on the transmission network. And the strength of the voltage disturbance is on the horizontal axis, with the most severe events on the right. You can see there's a very clear trend. As we get more and more severe voltage disturbances, we're seeing larger and larger proportions of PV disconnecting. And we've also verified this with bench testing, looking at how inverters behave under laboratory conditions through an ARENA project with the University of New South Wales. So all of this has been now incorporated into our PSSE and soon to come PS card models that we use for analysing the power system and how it behaves in these disturbances. Next slide. What we found in incorporating all of that behaviour into our models is that if we have a severe but credible fault at certain locations in the grid, that can lead to significant disconnection of distributed PV. And when the PV levels are small, you actually see load disconnection as well, and the load disconnection will usually be larger than the amount of PV disconnection. But as the level of distributed PV increases, we see much more PV tripping off than load. So it becomes a net generation contingency. And importantly, this can happen in association with the loss of a generating unit. So you can have a certain kind of a fault that disconnects that generating unit and will also disconnect a large amount of PV. So it's adding on to our largest credible contingency that we need to manage. And that has all sorts of flow-on effects for power system frequency management and so on. So the table here is showing you the amount of PV, the net disconnection of PV that we expect or that we've projected based upon these models in South Australia, Victoria and Queensland under two scenarios. The left columns are the central scenario from the ESU, and the right-hand columns are a sensitivity around that where we've got more PV and a bit less load. So it's a more extreme case. You can see that in South Australia, even in historical periods, we're looking at very large amounts of PV tripping off, around 100 megawatts or more. And the values in brackets there give you the range of uncertainty. There is some uncertainty around this. But we're already in the realm where when we're operating South Australia, particularly as an island, we have potential to see 100 megawatts or more of PV disconnecting. And that means that we are now in the realm, it's in some periods where it's almost impossible to maintain frequency above 49 hertz for those kinds of contingency sizes. And that means that we no longer have the ability to operate that South Australian island in a secure state if that islanding occurs at a time of high distributed PV generation. Now, that's an unlikely coincidence of things, but it can happen. And so something that's very important that we prepare to be able to manage the system. And we've got work underway to do that. These numbers are also showing you that in Victoria and Queensland, the contingency sizes we think are very small at the moment, but they do escalate very rapidly from about 2021, 2022 onwards. And they become very large very quickly as we get more and more PV installed in the system. So this is saying that we've found this issue in time, that if we take prompt action, we can address it, particularly in Victoria and Queensland, before it becomes a pressing issue. Next slide. So what do we need to do to manage this? There's a whole suite of things underway. The first thing is to improve the performance of the distributed resources themselves so that they don't disconnect in these sorts of disturbances. So the main mechanism here is Australian Standard 4777, AS 4777. So there's a review process underway, which Taru is actually leading, working to improve those standards and make sure that inverters ride through in these kinds of events. We're also accelerating the introduction of particularly the voltage ride-through component, which is particularly what we're talking about here in South Australia, where we know that that's a particularly urgent issue. We're also working to improve compliance with those standards, because from other evidence, we've seen that around 30 to 40% of inverters look like they're not behaving in a way that's consistent with the standards. So we need to address that as well as improve the standards themselves. And we're working with distributors on their connection requirements as well to make sure that when they're adding additional protection systems, they also ride through these disturbances and aren't interfering with those ride-through requirements. Additional network obviously also helps, particularly in South Australia when Project Energy Connect is commissioned, connecting South Australia into New South Wales via another interconnector. That significantly reduces the probability that we'll have to operate South Australia as an island and reduces the incidence of these problems. And finally, we're also using network constraints to manage these issues. That largest contingency appears in a bunch of different constraints, and we're now managing flows on the Hayward interconnector to manage that potential contingency event. Next slide. So the second issue that we've identified is just having enough load to operate the minimum units that we need, particularly when we're operating an island, as we do need to sometimes in South Australia. We need to have on a certain number of synchronous units to provide system strength, inertia, frequency control, and voltage management. Those are the essential services. And at the moment, that does require that we've got a certain amount of synchronous capacity online. The chart on the right is showing you the amount of load that we need in South Australia to operate a secure system that has all of those services just in the South Australian grid if it's operating as an island. And there's a bit of a range in the box and whisker you can see there because of the different unit combinations that might be online. So if we're using the very, very bottom combination, we may get away with around 200 megawatts or so. To run that unit combination. But we do see very often units are on outages, particularly over shoulder periods and low load periods. It's a very good time for units to take outage for maintenance. Or they may be damaged in a storm or another event that's actually what's caused the islanding in the first place. There's all sorts of reasons why we need to be able to have some flexibility to operate with different unit combinations. And with some of those unit combinations, with the larger units, we need much, much more load, upwards of 550, 600 megawatts or so to run those unit combinations with all of the required services. The red line that you can see across the middle there is the minimum demand that we've experienced. This actually happened last Sunday. We got operational demand down to 379 megawatts in South Australia, which was a record low. And you can see that that is well down in the range where there are many unit combinations. In fact, the majority of unit combinations in South Australia that cannot run down at that low level. So this means we're very restricted in operation if we happen to have an islanding event in these low load periods. Going forward, you can see in 2021, the level drops quite a bit. That's because of the introduction of the Electronet synchronous condensers, which help to provide a lot of those services, particularly system strength and inertia. And that means we can operate with fewer units online and still meet those requirements for a secure system. So that helps a lot, but it doesn't get us all the way. There's still a certain amount of demand required beyond that point. Let's move to the next slide. Sorry, this wasn't the slide I was expecting. Let's jump back one through. Sorry. So the actions that we take in order to manage this involve putting in place the capability that we can turn down the PV systems, distributed PV systems, when we need to. And this would be done under very rare circumstances. It's really just if we've had an islanding event or some sort of line outage or an abnormal circumstance on the grid. And in those circumstances, we need to very quickly recover the amount of load that we need to run the units that are needed. So most of the time, that generation can run freely. It can do whatever it wants to, and customers can have full value from exporting their power. In the vast majority of periods. But in order to be able to run a secure system, if we do have these extreme network outages, we need the ability to turn them down in those periods. So we've been working with SA Power Networks and the SA government to put those capabilities in place very quickly. And a lot of that has now come online because, as you can see, we're dealing with these very low minimum demand levels happening. And we expect those to keep happening over this coming spring. So that capacity is coming online to help us manage that. So let's jump to the next slide. So we've also now done analysis looking at this in other regions. I won't go through all of these in detail because we're running short on time, but you can find that in the ESU. The headline messages are that in South Australia, as we've seen, this is quite pressing. In Victoria and Queensland, we also need to act quite promptly to implement these capabilities to be able to turn down PV when required, because they're on the cusp of the similar issues coming. New South Wales and Tasmania look like they're further away from these issues. But it looks like it's timely to really be looking at putting in place these capabilities that we're going to need to run the secure grid across all regions to make sure that we can run a secure system when we need to. Next slide. So very briefly to finish up, the final issue we've been looking at is the capability of our under-frequency load shedding schemes. So under-frequency load shedding is our safety net, which is designed to arrest very severe under-frequency events. It works by tripping off load blocks to help stop the frequency decline and stabilize the system so we can then recover and reconnect those load blocks. And it's very important, particularly for managing separation events in South Australia, to catch the system if we do separate. There's a series of issues we've identified with under-frequency load shedding being impacted by distributed PV. It reduces the net load on those circuits, so we've got less load to trip to arrest the frequency decline. And we eventually see circuits go into reverse flows, which means when you trip that circuit, you're tripping a generator rather than a load, and it actually exacerbates the frequency decline rather than helping to correct it. And finally, the distributed PV itself actually fights against the UFLS scheme because it's tripping off as the frequency drops. And so it's making the challenge even harder. So there's a whole suite of actions underway to manage this issue as well. We're increasing the amount of load in the under-frequency load shedding, putting as much load in there as we can to try and boost the capability. We're introducing dynamic arming of UFLS relays, so it will be much smarter and more responsive. We're putting in place a new constraint, which will be happening very, very soon. That's in the final stages of working through our process at the moment to limit flows on the Hayward interconnector when we know that the under-frequency load shedding is not adequate and increase the probability of forming a stable island. And we're also looking at these frameworks under the national electricity rules and how they need to change longer term to put in place the enduring frameworks we're going to need. Next slide. So to finish up, there's a whole bunch of work going on at the moment. We're collaborating with stakeholders on the design and implementation of all of these mitigation actions. The analysis itself is ongoing, and we're learning more and more as we go. And we're continuing the development of our tools and data, which we've gotten them to a good stage now, but there's constant refinement that needs to be done to improve them as we learn more. So thank you for your time. I will hand it back to Mark.
Sorry, Mark, I think you might be on mute, or we can't quite hear you. Oh. Sorry, Mark, we still can't quite hear you.
No, I better let him know it's not working.
Yeah, unfortunately, it's not working. So, so maybe, David, if you wanted to maybe give a small introduction to yourself.
Sure. Yeah, look, great presentation, Jenny. I really like that. And if anyone was watching, they probably saw me furiously nodding because Horizon Power operates 38 microsystems or microgrid systems that are geographically isolated through regional West Australia. And we've been a microcosm for these sort of problems for about the last 6 or 7 years. And so it's really, I won't say gratifying to see the larger grids suffering the way we have. That's not what I mean. It's just interesting to see the way technology is moving and people have had a chance to think of better ways to tackle these problems. So look, I think it probably is better if I just crack on. My name's Dave Edwards. I'm the Digital Strategy and Innovation Manager at Horizon Power, and I'm the Director of the Carnarvon Trials, which is what I'd like to talk to you about today. So Jenny, do you want to, it's not Jenny, Tara, do you want to move on to the preso? Next slide. You can go next. Okay, so look, thank you very much, everybody, for giving me the chance to talk to you about the trials and give you an update. I'll be talking specifically about trials 1 and 2, which are ARENA funded, and they include our academic partner, which is Murdoch University. And we are working with them to provide a series of research and engineering-based reports and recommendations that are supporting our deployment of DER management technology and hopefully helping us move towards a very high penetration DER environment. Next. Like many of you, we've seen generation grow over the last few years to become the largest single generator on many of our networks. Solar PV has changed the load profile presented to our power stations, and the withdrawal of premium feed-in tariffs and the arrival of batteries will change it once again. So how do we address some of these challenges whilst preserving system stability, power quality and reliability, and what methods can we use to de-risk this future state? One thing we do know is that we won't find the answers to these questions in the way that we've done business over the last 50 years. Next slide. The Carnarvon DER trials are seeking to understand the impact of cloud events and renewable energy variability on the way that networks operate. How does weather affect renewable energy generation and customer node? And if we had visibility of DER performance and control over some parameters, how could we use that information to de-risk the impact on power quality and service delivery? And questions like, can we leverage visibility and control of DER to manage the potential for a very high penetration DER future and reduced costs? Our hypothesis is that we can use feed-in management to release more network hosting capacity for DER. Next. So we started to look at the principles of Industry 4.0 as a means of gaining visibility and control of DER. And by exploring orchestration of DER to maximize their value to the power system and how we could actually exchange that value with customers. Next. Industry 4.0 gives us a chance to rethink our service delivery model and imagine what a future power system could look like. This slide shows a typical transformation pathway from a core physical product to a digital ecosystem. And so we started to explore what steps we could take to evolve from a physical product to a digital ecosystem with customers at the heart of value creation. How could we transform into a digital utility with an ecosystemic approach to energy delivery, where the customers become an active participant in providing energy to their community? And then beyond that, through digital channels, how could we transform that relationship to one of a trusted partner? Next. So what we did in Carnarvon was we recruited 82 customers to gather data about what was actually happening on the network. And we used the WattWatcher IoT product, and we used solar analytics as well. Separately metering PV from load on 82 premises to uncover the true load, which has been masked by PV for the last decade. This slide shows how the data is collected into our database in Bentley, where it's blended with advanced meter infrastructure and SCADA data from the power station, as well as meteorological data. Next. So this visualization shows what we've collected from the data from the individual PV systems of the trial participants. Each coloured bar represents a renewable energy system, and it's represented by the output. The PV systems are different sizes, and so they're shown here scaled from 0 to 100%. And together they're representative of approximately 3 megawatts of PV that's currently connected to the network. The data has been combined with sky camera and meteorological data, and shows the variations in solar generation as clouds move across the town on a typical cloudy day. This visualization shows one day compressed into a minute and highlights the number of cloud events and the depth of impact on the renewable energy generated in one day. It also shows the number of very interesting things such as the passage of clouds across the town and the PV edge effect that affects PV generation, which can be seen in the top of the final graph, which are those extra spikes that are going above what you would imagine is the normal curve. Next. Then we installed 10 PV battery systems and upgraded 6 existing customers' PV systems to include a battery and also a reposit box. And the aim was to explore how we could limit the amount of energy that was flowing into the network from managed systems, but not to limit the ability of customers to meet their own energy requirements. Next. So using the reposit box, we've been able to test visibility and control of PV and energy storage within a virtual power plant framework. We've been exploring virtual power plant technology so that we can use DER to assist power quality rather than cause problems. And we're developing feed-in management techniques and principles of operation that preserve value for customers, as well as testing battery optimization and innovative tariff models with methods to exchange value with customers for activity from their DER that doesn't pass through the tariff meter. So typically this could be a customer discharges their battery during the peak demand period, which is entirely consumed behind the meter and therefore remains invisible to the retailer. Next. So in this visualization, you can see it should start moving in a sec here. This is the same PV systems that we're monitoring, but this time we're looking at voltage on a cloudless sunny day. The bars are green when the voltage is below 254 volts, and they turn red when it's over 254 volts. And the distribution graph from our research partners at Murdoch on the right-hand side shows the number of over-voltage events that were detected using the WattWatcher data. You can see that the number is quite high, and this is a problem, as Jenny just mentioned, that's becoming apparent nationally and internationally as solar and PV penetration increases. Here in Australia, there's been a great deal of discussion around using inverter control at a primary level by adjusting response curves and settings within the inverters themselves. So we started to explore how we could use reactive power droop curve settings to manage network overvoltage events. And what we discovered was unexpected and initially very surprising and interesting, but at the end of the day, it's quite obvious, and I'll explain why in the following slides. Next. So this map on the right-hand side is actually zooming in on part of the Carnarvon network that you just saw with the undulating bars. The slide shows 6 reactive power droop curve configurations that were tested on a group of PV systems, all situated on one feeder. And the map on the right shows the properties on that feeder. The blue properties have no PV systems. The yellow properties have unmanaged PV systems, but they're not part of the VPP that we're testing. And the red properties have PV systems that are managed by the virtual power plant platform. The 3 graphs on the upper right-hand side of the slide show the maximum power exported from this feeder back onto the main network at a single point of connection. The other box shows the steady increase in the amount of reactive power absorbed by the inverters under test, and then the next one is the average minimum and maximum voltages on the feeder during the test period. Next. So what you'll see in the following visualization is that the inverters under control actually do a very good job of importing reactive power to reduce voltage. But at the same time, they create an operational advantage for all of the uncontrolled PV systems, who then raise the voltage back up so that they can export more power. The end result is a negligible reduction in the maximum voltage on that feeder, but an appreciable increase in the amount of renewable energy exported onto that feeder. Next. So this slide shows one of those unmanaged PV systems on that particular feeder. Prior to the reactive power control, the inverter in question was unable to operate effectively because of the high volts on the feeder. But during the reactive power control experiments, the performance of the inverter was markedly improved because the voltage on that part of the feeder was improving. And this raises some really interesting questions around the usefulness of Q control to manage network voltages while we still have a significant fleet of older and unmanaged PV systems that remain connected to our networks. Next. What we've observed during the Carnarvon DER trials is that more than 50% of the inverters that we are monitoring are not working as well as they could, which is unsatisfactory both for the customer and the network operator. Loss of PV generation is a lost income or a saving to the customer, while frequent inverter trips due to high voltage exacerbate the fluctuation factor of renewable energy generation manifested to the network and ultimately to the power station, thus reducing hosting capacity. We've begun exploring if it's possible to improve power system performance by physically rebalancing the network through the reallocation of single-phase PV systems to other less congested phases. And what we're doing is we're applying k-means clustering analysis to our advanced meter data to identify the phase allocation of single-phase PV systems and how much they are contributing to high voltage events. In combination with that, we're doing an audit across the entire town of Carnarvon, looking at all of the inverter settings in the town. And we hope that by combining these two pieces of data, we can combine an effective method of bringing the network back into balance by reallocating those single-phase inverters to less congested phases. The aim is to identify value creation for customers and the network operator before we have to resort to feed-in management of the individual PV systems. Next. Lastly, I'd just like to talk about the use of batteries. What we did with the Reposit product was we were experimenting with time of use tariffs, which were applied in the Reposit box of each system that had a battery. The Reposit box was allowed to control the charge and discharge of the batteries. And what it did was it pre-charged the battery before 7 a.m. if it estimated that the solar would not provide enough charge on the battery to carry the household through the peak period. And it does this by using machine learning of the customer daily usage patterns and then the PV production, and it applies a weather forecast signal which is provided by Reposit. What it does then is it discharges the battery to match demand during the peak period. And what we were able to do by moving this particular customer, I mean, we kept them on the same tariff during the trials, but for the sake of the system, it thought it was on a time of use tariff. We were actually able to reduce their peak time network load by 64% and reduce the network average peak load by 67%. And assuming if that customer was actually on a time of use tariff, we would have reduced their bill by 36%, which opens up all sorts of possibilities around how we might be able to share some of that saving as an incentive for customers to invest in batteries. Okay, last slide. So just to summarize what we've been learning through the trials, we finish in February next year. We'll be publishing all of our findings and lots of nice reports and visualizations. But what we've done along the way is we've been able to develop a framework for very complex power system analysis using Power Factory. We've developed a lot of knowledge which we've been able to transfer over to the Onslow system, which is going hydrocarbons off in the next few weeks. We've been building core competencies in the management of DER in VPP environment in microgrids. We've got a much more informed customer-centric approach to DER orchestration. We've got a lot of experience in building very large data sets, currently at 150 billion data points. We estimate by the time we shut the project down, we'll be at 210 billion data points. We've commenced knowledge sharing directly with the Alice Springs Future Grid project, which we see as a continuation of our learnings into a market environment. And I was interested to hear what Jenny said. Well, we noticed that a lot of the brand new inverters were not behaving as we expected them to behave, some very strange behavior. So we put one of the inverters into a lab at Murdoch, and we did a lot of very stringent testing, and that testing report is being provided to the AS4777 review committee. Next slide. So that's me finished. Thank you very much for listening. I hope you've learned something interesting. If you want to catch up with me, you can ping me on LinkedIn. I'm always willing to share what we've learned, and thank you very much for your time.
Actually, Mark, it doesn't look like we're able to hear you again. Thank you very much for that, David, as well. Mark, I can give you another.
My pleasure.
Thank you.
Mark should have learned sign language.
Can you hear me now? No?
Yes.
Oh, lovely.
You can. Oh, look, I'm so sorry. David, thank you for self-introducing. You did a great job, I'm sure. And thanks for bearing with us on that. It's the joys of a land of webinars. I guess so we've really gone from the national electricity market that Jenny's been speaking to, which is one of the world's largest interconnected systems. We've gone across the continent to Western Australia, to Horizon Power, which is essentially, as I say to my Californian friends, 5 times the size of California with the population of Pasadena. And now we're heading to the UK to Goran Strobovic, Professor of Energy Systems at Imperial College London. And Professor Strobovic is his extensive experience in advanced modelling and analysis, operation planning, security and economics of energy systems. So I'll hand to you, Goran. Thank you.
Thank you very much. I hope you can hear me. Yeah,
Great.
For invitation to this to give you an overview regarding the particularly these conflicts and synergies of distribution resources providing services for distribution and transmission network, and our modeling is being used significantly to inform regulator and the government, but also in Europe regarding this cost-effective transition to low carbon system. So if we go to the next slide, because we are pretty tight on time, this is just to remind you that the UK has got a very significant now commitment to reducing to have a zero carbon energy system, even in fact negative by 2050. And one of the core issues which we've been working on is to how do we facilitate cost-effective transition to that system. And this is just a diagram showing the benefits of flexibility and smart control in terms of what we mentioned, transition to digitalized world, that it would, beyond 2030, that if this happens, that we would have a more than £8 billion per year savings. To give you a feel, this is about of the present electricity market overall costs are about 24, so it's 1/3 of the cost could be saved if we make this smart control and shift to the digitalized world. One of the important aspects, and you can see different components, but what is, if you look at just the on the right hand side, this 8 billion, you can see that the biggest one is the red, which is the in fact reduction in savings in generation costs associated with low carbon generation costs, which means if we've got this smart control, we demonstrate that we would be able to meet the carbon target by building significantly less of amount of low carbon generation. In the UK, there is distributed, but it's mostly centralized, nuclear and offshore wind. We demonstrate we will be able to, that's where the savings in terms of the overall benefits would be in reducing the amount of low carbon generation to meet the carbon target, building 10 gigawatts less nuclear and 15 gigawatts less offshore wind, for example. And this is something which is, as I say, it is important just to have that in mind. But I'm going to now, if we go to the next slide, just to illustrate regarding this issue regarding the control, because there is a significant shift of the generation from from traditional generation from transmission to low distribution networks. This is just a sketch of kind of north to south system. You can now see that where we are moving, there is a shift, in terms of generation going, renewable generation going towards the distribution network. And also one of the core aspects where the UK is now having a very significant activity is regarding the network design standards, is that we are shifting from delivering security supply, from what's called in here, from redundancy in assets to intelligent control of distribution energy resources. And that is where the big challenges are. You can see just here, there is also a significant novelty and the control systems at transmission level, but there is also at the distribution level. But where one of the important new developments is the interaction between distribution control and transmission control. If you go to the next one, please. You can see that there is in here the kind of link between the distribution and transmission control, because the sources of control are shifting down to distribution networks, while we've got a retirement of conventional generation and transmission network, which is historically being used to provide the control of the national transmission network. Given this, there is now very significant interest into the interaction between distribution system operators and transmission system operator, all our, and the system operator. And there are massive challenges because the complexity is very significantly increasing of this. And there is also, as already been mentioned, Jenny, regarding for example, regarding the making sure that the system is resilient. And you may know that there were some, big events last year in the UK, which was similar to what Jenny was saying. This was the frequency drop-driven outages and so on. And also there is now in the UK very government, and part of that work is to fundamentally change also the standards. And there is what was mentioned earlier. For example, there is now an analysis demonstrated if we, for example, can live with bigger voltage deviations, that would make massive savings in terms of network reinforcement, for example. And also there is also interest in seeing how the frequency regulation standards could change, because again, for example, rate of change of frequency is one of the big items in the UK. But if this can be a bit relaxed, then you could potentially make billions of savings, because because the standards will be relaxed. So that's a very big activity in the UK. I'll just give you a quick example of two. If you go to the next one, please. We're running out of time. This is a demonstration project where distribution resources were coming in a particular area of distribution networks. We won't go into details, but this is just showing that these red lines in here represent the requirement for network reinforcement under the historical kind of passive approach, and that is where the kind of passive side. And in this particular case, it turned out that the it says in here what the investment costs will be required in a traditional approach. If we go to the next one, this is the same diagram showing just that the massively reinforcements have been avoided by applying smart control. And in here we've got active network management. We've got also application of dynamic line rating. You can kind of see some of these shadows in there. So that you've got smart control. It turned out for when wind is potentially may cause the overload of the line. When it's windy, actually the overhead lines are cooling, so you can actually make use of that and avoid network reinforcements. And also, what was interesting, for the first time, quadrature booster phase shifting transformer was introduced in the distribution network to actually control the flows, which was never done in the past. And the savings in terms of the, there was, more than only 1/3 of the costs was incurred by having this. We go to the next one, please. This is just to again highlight. This is a UK a bit specific, is to do with this whole systems approach. So this is showing that on this diagram, and the whole point is about how do we balance the national and local level requirements and services. So you can see on the left-hand side that if we use distributed resources and we only focus on distribution networks, you can see there will be, in this particular case, kind of around 2 billion savings, mostly to do with avoiding reinforcement of distribution networks, but also to provide some services at the national level. If we ignore distribution and focus on transmission only, the national level, you can see that the overall benefits increase, but go to details, the distribution network costs will be actually significantly increased, because we are going to then need to reinforce distribution to support national level. But if we do a coordinated approach, when we properly coordinate local and national level objectives, you can see that we are significantly increasing the benefits, and also the amount of distribution network reinforcement also minimized. And this is where we need to move on. And currently there is a very significant developments in terms of the market regulatory framework, because because now there is distribution network operators would not be only focusing on their networks, but they would need to maximize the access of distribution resources to provide services to both local networks but also at the national level. And this is something which is under the big development in the UK, and potentially it's maybe at the leading edge. We go to the next one. Just to illustrate another demonstration project called Power Potential, which is in southeast of the UK, England. In here, and that's to do with the fact that in this area there were a number of conventional generators, coal and gas, which are but the system is near this a bit of kind of boundaries and so forth at the transmission level. But they're being retired, while there is a significant increase in the distributed resources in the southeast of England. And the question is, how you can see in here kind of virtual power plant concept, how these resources can they be used to provide services to the transmission network. And in this particular case, the focus was on the voltage control, because that was a big area. And also there is linked with interconnection here, so there could be potentially flows, plus minus 2 gigawatts. And that makes very significant issues regarding the voltage control transmission level. And the issue is how these resources can be used to support that. If you go to the next one, these virtual power plant concepts. And this is just to show. This is just this. You can see the function of the cost function regarding the on the x-axis is the reactive power. And what this is showing, that we can use these resources to kind of to absorb or inject reactive power from the distribution network to transmission. But you can see in here that there is in here some amount which can be delivered at zero cost. This is just assumed that the distribution network operator, distribution network operator by making the smart control distribution networks, by, for example, managing tap changing of the transformers, could actually significantly reduce, we put it in as zero, cost to transmission network voltage control. And this is again just showing that the distribution network operators, by making control of the local system, would be able to enhance the provision of security supply at the national level. And this is something which we, as I say, is moving forward to get the market regulatory framework to make that happen. Go to the next one, please. This is one, again, to illustrate how important in some of the areas, this was in kind of in near London area, regarding the use of distributed resources, when it's demonstrated in fact that it would be in fact worthwhile to potentially reinforce distribution networks. You can see the negative costs are kind of, this is where distribution capex is, in order to make savings at the national level. And this is again the need to start balancing synergy and conflicts between local and national level requirements. If you go to the next one, please. Yeah, this is just to say that we are on the left-hand side is the kind of historical design of the system. We are moving now into very much integrated system, and there is also very, given these challenges in terms of climate change, security, supply, development technology, and so forth, into much more integrated approach, where it also start now including also electricity system, but not only electricity system, but also, for example, there is also interaction with gas and transport and so forth, so that we can actually make the much more cost-effective transition to low carbon system. And that's something which is, again, in terms of the regulatory market framework, is very much growing on the agenda. We go to the next one, please. This is a sketch in terms of the market transition, showing on the left-hand side, yesterday's system, when everything is done, everything is driven by the, production costs is the blue one, the electricity market. While we've got CFDs, is contract for difference for low carbon generation, and also capacity market and system services are very small. This is showing that, in 2030, that the operating costs of the system is going to reduce more than 50% because of the shift from conventional generation more to renewables. And we would need to have much bigger investment in these generators, but also we demonstrate that the system operation the cost could potentially increase more than 10 times. And the question is how now we need to shift from where we yesterday were to a new future. And one of the core aspects in here, which I think is still not yet being done anywhere in the world, and but hopefully it's getting on the agenda, which is to align the market design with the low carbon agenda. And as mentioned at the very beginning, where the biggest benefits are, but currently the flexibility resources cannot access those benefits anywhere in the world. And this is something which is now getting on the agenda. I think it's going to be very important. And if we go to the next one, it's just a kind of some of the summaries and the questions as to where the developments currently are. Yeah, this is showing that some of these in terms of the incentives to make that work, so that because currently there is we need to move into this digitalized world, and there is a need for regulatory framework which would make that happen, and also provide rewards for the organization, which is now happening. Also, this whole systems approach is getting very big on the agenda in terms of the local versus national, and it's also this strategic investment, strategic impact of the interaction between transmission and distribution is very important. And there is also now very significant developments regarding regulatory and policy framework to actually make that happen. And at the bottom it says to link electricity market design with low carbon agenda is one of the biggest challenges which we are currently facing. Thank you very much, colleagues.
Fantastic. Thanks so much, Goran. That was a third fantastic presentation, and just some really great insights from the other side of the planet, really, and some quite distinct and whole system perspectives, which is awesome as well. All right, so we're going to be bringing up the questions that have been coming through on Slido now, and we'll deal with them over the next 20 minutes or so. And as Taru mentioned, we will run over, obviously, a little bit. Thanks for bearing with us on some of the technical issues at my end. Apologies again for that. But if we get into it, and please feel free to enter in questions for the latter speakers as well, for David and Goran as well. But we'll start off with some questions, I think, for you, Jenny, especially. So Peter Newland's asked a question there around, I guess, some of the flow-on impacts of some of the dynamics that are happening in terms of whether solar installers will now likely sell batteries to customers, enabling them to island in the events where AEMO wants to disconnect the solar. In his view, this could mean that AEMO loses the generation and the loads, which means no benefits have been achieved. What are your thoughts on that potential situation?
Look, I guess it's a long-term possibility that customers really do decide that they want to have those sort of backup systems so that they can just separate off from the grid and run as their own little island for periods of time. It's not the challenge we're dealing with right now in terms of large customers choosing to do that. And I'd hope that in future we have the right measures in place so that customers have the right incentives and benefits.
Great, thanks, Jenny. All right, question for David. How much real power curtailment occurred at the sites where reactive power droop was enabled?
Can you hear me now? Okay, because I was muted, like everyone does. Right. So look, it's pretty difficult to estimate because the droop curve only turns on in the middle of the day when the solar installation is at its highest or when you've got a problem on the network. And the only way to measure the amount of real power that's being curtailed would be to have an identical system right next to it and measure the drop in renewable energy generation. But what I can tell you is that because we've got smart meters, we were able to measure the amount of reactive power that's imported, and that was important to us because if you think about it, for years we've been rewarding customers for exporting real power into the network. Maybe we could start to reward them for importing reactive power into their network, into their inverter. So it was really just to test the action of the curve, and I'm afraid I don't actually have a figure, but I think if it only occurred during times of peak solar installation, during the sunniest periods of the year, the amount of real power that's lost by the customer could be equivalent to having dirty panels or having shading on their system for part of the day. It's that order of power loss.
Okay, thanks, David. All right, another question for Jenny. Where are we in using demand management to load shift, for example, HVAC or air conditioning? So shifting it forward into high risk, low load zones.
Yeah, certainly load shifting is a really obvious solution. If you don't have enough load, rather than turning off PV, let's get more load to actually use all of that energy. Longer term, that's certainly going to be where we need to go, because on a daily basis, we're going to have very, very large amounts of PV. So it's really important that we set up the market frameworks and that the technology starts to come to the party where customers can actively shift their load. At the moment, it's not a practical option for very large capacities of load, and it's not even close to enough to manage the sorts of amounts of PV that we're dealing with right now. So we've come to think of it as two quite separate things. There's some immediate measures that we need to put in place that are for managing very rare emergency events on the grid where we have line outages. And for those periods, we do need the capability to be able to very quickly turn off large amounts of PV, but it's extremely rare that we would be doing that. And it's very much a backstop security mechanism. And quite separate to that is to be able to run the grid down the track when this starts to become a daily occurrence, to allow customers to get maximum value from their assets and avoiding curtailing regularly. We're going to need that load shifting to come forward. So we are looking at certain amounts of load shifting in the immediate future, but the quantities are quite small in what we can do immediately. And long term, we need the market frameworks to unlock all of that.
Yeah, great. Thanks, Jenny. Actually, I might just extend that question to Goran, given that, Goran, there's an extensive amount of work in the UK on demand-side flexibility, and you've sort of touched on that whole system approach. Did you want to perhaps just speak to that, just to bring a UK perspective to how demand-side flexibility is being expanded?
Yeah, that's a very important point, and there is definitely very significant interest in the master flexibility. There is also now interest in, for example, also at the end use of smart appliances, and also to try to see how these appliances can be used. For example, there are smart refrigerators or smart dishwashers. So, refrigerator would, for example, if there is a reduction in frequency because of the very large loss, you could have a potentially switch off your refrigeration for some time, but there will be no compromise on service quality. Kind of, as you say, all your beer will be cold, will be good cold, so that you can actually support, for example, frequency regulation. But there is also similar now aspects. There is a very big activities now also in terms of electrification of transport sector. It's a very big activity. For example, London wants to electrify all buses and taxis in the next 10 years. And there is now very big developments and the demonstration project in terms of, for example, vehicle to grid concepts, which again, and also providing both network service, but also providing frequency regulation. So if there is a loss, you would have the electric vehicles which are connected. They would inject for a few minutes power so that the frequency will be maintained. So this is it's a very much very, very big emphasis in terms of an interest in terms of seeing how the distributed energy, kind of how flexible demand can be used to support and provide security and resilience to the future system.
Great, thanks, Goran. Thanks, Jenny, for those responses. Another question from Peter Newland. Should there be an immediate focus on tariffs to reduce prices in the middle of the day to encourage business to use more energy, grow their business while adding more load to the system? I guess at those critical points. Probably one for yourself, Jenny, and maybe David, you might have a perspective on that as well.
You first, Jenny.
Yeah, I think we covered a lot on load shifting in the previous question, so I don't have too much to add to that.
Okay, so in WA we've just shifted into a new pricing regime it's called from REBS, which is Renewable Energy Buyback System, to DEBS, which is DER buyback system or buyback pricing. And what that does is that prices the value of renewable energy during the middle of the day much, much lower than it has been before. In some cases it's like 4 or 5 cents. But places a much higher value on renewable energy towards the end of the day. So I think it's worth considering the fact that a lot of the issues that we are dealing with today as energy systems operators are because of the price signals that we've been sending for the last number of decades. And we're sort of patching up a bit here, and we're trying to manage something here, and we're trying to do something there. But a lot of the discussions that we are having today, it's essential that we have some kind of tariff reform somewhere down the line. I think the reason that we haven't had tariff reform up till now is because we as network operators and we as utilities haven't figured out how to support the Minister for Energy in the tariff reform space so that he can actually start that conversation without sacrificing his political career. And for many years, it's been utilities pushing the idea of tariff reform on customers. We need to find a way of turning the conversation around the other way so that the customers, we do a ground-up approach to tariff reform, and then we end up with a solution that is politically palatable.
Great, thanks, David. I just want to, given that this is such a central issue in so many of these topics, Goran, you, again, from a whole systems perspective, you touched on, I guess, the transformation of the market architecture. I wonder if you've got any sort of quick reflections on the transition from perhaps more advanced tariffs into, if you like, a market-based solutions, distribution market models that enable that kind of valuation of demand-side flexibility and services.
This is absolutely a very critical question indeed, and there is, given again some the evidence provided, which we also involved with, that this flexibility is the core for transition to cost-effective transition to low-carbon system, but the present market is not really yet aligned with that. And now there is quite a big interest in terms of having more cost-effective and cost-effective charging mechanisms, and also the ability to also to have for example, that local resources can also support frequency control, and there is now significant interest in reducing the sizes of the minimum size of the plant which can go into this, so that that distributed resources could potentially enter this. And the analysis demonstrates, for example, that the flexible consumers who would be providing these services, but without any compromise on the service quality through these home energy management systems, which are now being also in trial, that their bills would be less than 50% of the bills of the consumers who do not want to engage, for example. So given that we are moving into this low carbon agenda with renewables, the way in which we consume energy would in fact be more critical than the amount we consume going forward in terms of the overall system. And this is where there is a significant interest in the UK and also in Europe, which I'm aware of, regarding to make the market, the network charges and so forth, all of that to be much more cost reflective, and to provide proper signals to the users, so that they can make choices to how they should respond, so that we can make so we can have the consumers in the center of the decision making process, which is the whole point of the market. So there is a very, very significant interest to make that happen.
Great, thanks, Goran. All right, next one. You just need to take a bow, David. Coolest visualization award goes to you, so well done.
No, hang on a sec before you go any further, Mark. I must confess that it wasn't me. It was a guy called Owen Lamont, who now works for Synergy. I'd encourage you all to go and follow him on LinkedIn. He's very talented visualization data scientist. So Owen Lamont, follow him on LinkedIn. He does some very cool stuff.
Thanks, David. All right, question for Jenny. Whose role is it to ensure inverters comply with standards? AER, question mark.
So it is a good question, and actually there's no really clear answer on this one. So inverters have to pass accreditation testing. They get that done by an independent testing house in order to be certified as compliant with AS4777, and that's all then collected by the Clean Energy Council to have that list. And the network businesses then refer to that list that you have to be accredited with AS4777 to connect to their network. So there's possibly, arguably, some role for the network businesses themselves in perhaps auditing what's connected to the network and making sure that it is actually set on the right settings. But none of the networks are really actively doing that kind of auditing at the moment. There also might be a role in there for the Clean Energy Regulator, who do have a role around checking electrical safety, particularly for larger systems, and they do some auditing to make sure that systems are being installed correctly, but up to date have not had widespread auditing schemes, and there's no real penalties applied for installers that aren't installing systems correctly. So it is actually a gap in the framework at the moment that needs to be addressed, and it's being looked at by the ESB as part of their DER governance work.
Great, thanks, Jenny. Another question for you. Under frequency load shedding, there's a huge opportunity for residential voluntary load shedding. Far better, the question is, than DNSP tripping, as in distribution network service provider. For those of you who are overseas, distribution networks tripping whole zone substations in emergencies, question mark.
Yeah, so we're definitely heading in the direction of much more granular load shedding. There are some options that are sort of in a trial phase where you can actually have separate tripping of particular loads at customer sites. But it is quite novel technology because these are things that it's quite different to a manual load shedding process. It needs to have a relay that can activate in hundreds of milliseconds because we're talking about very severe disturbances here where frequency is dropping very, very rapidly. And we only have about less than a second to act. So you do need quite a high quality relay to measure that. There's also potentially options with smart meter technology that may be able to have that capability in future. And we're probably going to have to head in that direction to have the sorts of responses that we need from these schemes longer term. Because when you shed whole substations or even whole feeders, we can't separate out the load from the PV as we're going to need to. So definitely a need for new technology and new thinking there.
Great, thanks, Jenny. All right, well, back to the UK. A couple of questions for Goran. I'll start with the second one there, which goes to the regulatory process in the UK. So the question is, has the regulatory process in the UK started to approve DNO, equivalent, I guess, of DNSP's DNO spending to uplift their digital architectures and management systems for the smart grid transition that you were taking us through?
Yeah, that's a very good question. It is. This is now, we are now entering into the second price control for distribution networks. Just kind of started now. It will be from 2023 to 2028. It's and the digitalized agenda and smart control is very core of that activity, and there is also significant incentives for distribution network operators to use smart control, for example, and avoid and displace network reinforcements. So they would be, rather than, again, as we discussed earlier, that the revenues historically were only on the investment to the infrastructure. Now the revenues are much more driven by the by in fact smart control and the best value for the consumers. So that is very, very much in the core. And also, although still to be discussed, there is a recognition that there would be need for, as mentioned in this question, in terms of to make that happen, and also the what we called in the UK DSO transition, which is that the distribution network operators will not be only looking after their local networks, but also enabling local distribution resources to provide service to the transmission level and make that coordinated approach working. That is very big on the agenda, and there would be now, this is what the power potential demonstrated, that there would be now incentives and revenues for distribution network operators to make that happen. And this is something which I think is, I've not seen that in other parts of the world where potentially UK is going to be a leader in this area.
Yeah, and just maybe a quick follow-on from that. I guess it's very interesting to see the level of attention to really the transmission distribution interface that you're describing, and really what seems like a very heavy emphasis on uplifting that capability at the distribution end with a view to the whole of system optimization, which I think is obviously a very significant shift in I guess, our approach to these things.
Yes.
Second question for you, Goran, refers to the Power Potential project. The question is really about whether that project utilises small-scale residential DERs, or whether it's primarily focused on medium-scale distribution-connected generators. And also, could you please comment on small-scale DER opportunities at the transmission level?
Yeah, this power potential is focused on the kind of medium scale. It is a kind of field-based solar panels and wind plants regarding renewables, and then using their resources in terms of, particularly in terms of power electronics, to be able to provide. This is kind of the focus, was the interest was on the voltage side, and there is definitely interest in using the end use distributed resources, not only generation but also, as mentioned, also the flexible demand to support transmission network. And there is a now very significant development. As I mentioned, it's much more focused on the currently on the for example, vehicle to grid concepts, which is to do with, we can call it demand side, but also there is a kind of demonstration project as well in terms of very local use of distributed resources, kind of, but it's much more kind of on the peer-to-peer trading, so that the kind of in the local area, the consumers can potentially get more actively involved in the management of the energy system. But definitely, as I mentioned, regarding the implications on the transmission network and also local distribution network, there is a very, very significant interest in how the demand flexibility at the end user level can be used to support that. And this is also linked, a little bit with, if there are solar panels and so forth, and if you again control the load at the local level, this would also make better use of the local resources, which would also have implications about transmission and distribution network.
Great, thanks, Goran. So heading into our last few questions, couple for Jenny. Were BESS options explored to increase minimum load in South Australia instead of installing syncongs to reduce minimum load level, specifically for stable operation?
So the synchronous condensers that are being installed in South Australia are not related to minimum load. They're being installed to provide system strength and meet those requirements, and inertia as a completely separate requirement. So it's incidental that they assist with the minimum load levels. In terms of using battery storage to manage minimum load, the batteries that we do have in South Australia are extremely valuable for minimising the amount of load that you need, because they provide frequency control services very effectively. And that's one of the most difficult things to manage in the island, to make sure that we've got adequate frequency control, particularly in dealing with these very large contingencies from PV tripping off. So what we've found, and the experience from the most recent extended island that we had to operate in January this year, was that the batteries, you really don't want to use them to be as a solar soaking up lots of excess energy to try and lift demand. What you want to do with them is keep them very close to their middle level of dispatch, so they've got their maximum flexibility to provide lots of frequency control services. So they're very helpful, but not necessarily in the way that you'd think. If you were going to try and use batteries just as a solar soak to lift the amount of load, they tend to only be able to absorb like that for an hour or two, given the way that they're designed, and then they're completely full. And of course, during the middle of the day, we need them to last for 6 to 8 hours or so. So it would be a very expensive option to try and build enough batteries to soak up all of this solar. A much, much cheaper option is just to have the PV capacity able to be turned down in those very rare periods when necessary.
Sure, thanks, Jenny. Just another follow-on question there. Refers to AS4777 standards. When would they be published? How much relevance do they have with respect, or is there with respect to IEEE 1547 and IEEE 2030.5?
So if it's okay, I might throw this question to Teru, who's leading AEMO's engagement with the AS4777 standard review. Are you happy to take that one, Teru?
Yeah, okay, I can take that one. I'll take my ESIG hat off and my 7 hat on. So pretty much, for those that aren't aware, in Australia we have put out the draft version of the 4777 standard, and that has since, the draft is, for public consultation has since closed, and we are working through that. So we are hoping at the moment, ideally, if we would like to publish this as early next year. with ultimately there is a 1 year sort of turnover period, which we're aware of, for manufacturers to upgrade their equipment and then ship it out to us and also get it tested. So then hopefully by early 2022, we'll have inverters with this new standard. In terms of how much relevance there is in respect to 1547, we have definitely been referring to that as an international source of how to set the standard. And so yeah, there's a lot in what we've been considering, because we have in this particular upgrade of review of AS4777, we have been looking at enhancing the autonomous response for bulk power system security. In terms of the 2030.5, though, that is something that we left out of the scope for this particular review, but something that we would be considering in the next round, which we would like to pretty much undertake as soon as this version is complete. Hopefully that helps answer the question. Cool.
Yeah, thanks. Thanks, Drew. That's great. And I think the kind of, in a sense, the broad topic of standards, visibility, monitoring, and so on really goes to that next question there from Tim Ryan as well. I don't know, Teru, if you had any quick additions you wanted to make to Tim's question there, just about, I guess, to what extent, and indeed to what extent that kind of visibility is being extended through the standards.
Yeah, in terms of the standard, we're not looking at any sort of detailed monitoring for each of the sites. I think from, I guess from AIM's perspective, we wouldn't sort of probably need it at that level of detail unless it was sort of doing some post-event analysis. But I guess we can do that from a subset. So I guess from an AIM perspective, we'd be looking definitely at a sort of more aggregated view of that. I'm not sure if anyone else would like to speak.
No, that's great. Thank you. All right, so we'll just do with the last two questions here. And David, I've heard rumours that implementing DERMS systems are a pretty simple affair. I know that's not the case, obviously. A couple of questions here. There's lots of lessons that I know Horizon's learned through the process there, and some great learnings. So with regard to the Carnarvon trial, did you explore the control of demand-side resources also within the DERMS implementation?
Okay, so I'll answer the next two questions together. For the Carnarvon DER trials, this was 1.5 years before we actually invested in the PICE DERMS package that we're using in our town in Onslow. So we actually built a small, crude DERMS package for the purpose of aggregating various different forms of data, coming up with the best solution for the trials, and then publishing that through an API to Reposit, who were the third-party aggregator of the DER. So we didn't actually go as far as testing demand side in those particular trials, although we have done it in Broome with the Smart Sun project, which Mark knows all about, and we are also doing it in Onslow. As far as the communications are concerned to the edge devices, we use the internet. We didn't use 2030.5 in that particular project, although we have done in subsequent projects. We left it up to Reposit to use their own proprietary protocols to talk to their Reposit box, which then used the SunSpec protocol to talk to the inverter devices. What we did was we used the internet, which made a lot of people's faces nearly go purple, but what we did was we built in a couple of extra features so that if the comms are lost to the Reposit box, then it would slowly ramp down to zero export. The customer would still be able to meet their own needs, but they would stop exporting energy onto the network. And then when the internet connection is restored, it was able to ramp back up. What we did over the course of the trials is we measured the availability of all of the internet connected devices, and it was in excess of 99%. So I think that proved once and for all that as long as you've got the right fallback, loss of comms features, the internet is a viable way of communicating with devices. Obviously, if you're working like 10 or 15 minutes ahead of what you actually need, it's useless for frequency control, but it is a possible way of doing it.
Great. Actually, I might finish with Simon English's question, which is a cracker, really. just goes to Jenny. For South Australia, what happens when low load occurs in the evening and there isn't PV to shed? For example, if batteries are supplying load residentially.
So I think this is actually very similar to the first question we had. There is a possible future where customers will be using batteries to supply most of their own load, and that will be an extremely different power system to the one that we run today. I guess what we're learning now is how we run with really high levels of distributed PV, and as we get that under control, we will then start dealing with how we deal with really high levels of distributed batteries as well. So great question, and I don't know the answer.
Great, a very humble response there. So lots of things that we're all learning. I think I'll finish with a quote from the new head of Google, who said, as a business, they needed to move from being know-it-alls to learn-it-alls. And I think today's session is yet another example of, I guess, that posture that we've all got to have as we navigate this future. Thanks so much to Goran from the UK, David Edwards from Western Australia, and Jenny Rees, located in, I think you're in Melbourne, Jenny, with everyone else who's, I guess, experiencing the second wave there. So thank you so much for your time, and to Roo and the AEMO team for hosting this session. Thanks again. I'll hand back to Roo with any final comments.
Not much more from me, just thank you all for attending, and if you would like to see the recording or register for other events, please go to the website. And thank you very much, Mark, for facilitating. Thanks. Bye.
Thanks, Mark. Thanks, Teresa. Thank you, panelists. Bye-bye.
Thank you, colleagues.